So, this is our second lecture for the topic motion in a plane. Today, before starting any new concept, firstly, I would like to go through quickly through the all the previous topics that we had discussed in the first lecture, just to maintain the continuity and to make you memorize what all we had studied. So, firstly, we have gone through the concept of scalars and vectors. That scalars are the quantities that have to be defined only by their magnitude, and no direction is needed to define them. For example, distance, mass, temperature, time, etc. Also, the rules of their addition, subtraction, multiplication, and division, they are very similar to ordinary algebra. Then coming to the vectors, we discussed that these are the quantities that have to be specified by both magnitude and their direction. For example, displacement, velocity, acceleration, giving no direction and only specifying the magnitude of the vectors will keep the information incomplete. We also learned that how to represent the vector in the textbooks and also in our writing. We also discussed that these vectors, they do not follow the ordinary algebra rules, and they follow certain other special rules that we will discuss in today's lecture in detail. Then we discussed about the position vectors and the displacement vectors. The position vectors are the vectors which are drawn from the origin to the final position of a point, denoting its final location. And displacement vectors, they come into role when a particle moves from one initial position to the another final position. That means when we join the initial position to the final position, we will get a displacement vector. And these displacement vectors, they do not depend upon the path which is taken. They only depend upon the initial and the final condition of final positions. Then we discussed the resolution of vectors. Resolution of vectors, where we had studied the very important concept in linear algebra, that is in n dimensions, any vector can be written as a linear combination of n basis vectors. These basis vectors, they can be any vectors, and we will get a linear, we will get the constants to define that linear combination. But we had also seen that in our Cartesian coordinate system, we choose the orthogonal unit vectors as our basis vectors. What we had defined as I and j. So I and j were our unit vectors in our coordinate system. Any other basis vector can be taken, but these I and j are convenient to take because they actually point in the direction of our coordinate axis. And we also wrote this expression. Suppose any vector A can be written in terms of any two vectors xa plus yb, where a and b are any other two vectors and x and y are the constants which are multiplied with these vectors. That is, this expression means the linear combination. Then we also studied that there are two ways to representation of vectors. There were two ways to represent the vector, that was polar coordinates, and the other one was Cartesian or the rectangular coordinates. So in the polar coordinates, we studied that we can represent any vector in the form of r comma theta, where r is its magnitude and theta is the angle which that vector makes with the x-axis. So when we define r and theta, we can simply draw that vector in the 2D plane. And in the Cartesian coordinates, we studied that we can define a vector as x comma y, where x and y, they are simply the components. The vector is resolved into its components on the x-axis and the y-axis. So x and y are the lengths of that components. Then we also discussed how to convert from one coordinate to the other coordinate, and we also saw this through an example. The same concept, they can be written down for 3D also. We also discussed those expressions. Then we practiced we practiced few of the practice problems also. Now starting with today's lecture. The first topic we will going to take would be equality of vectors. Two vectors A and B, when are they said to be equal? Let's first suppose we have first draw the two vectors. Suppose this vector is A and this vector is B. This is vector A, this is vector B. When are they going to be equal? In this case, we simply say that two vectors are A and B are said to be equal only if both their magnitude and the direction are same. That is, graphically, if we talk about when we shift the, let's suppose we are shifting B vector. When we shift the B vector, the tail of the B vector to the tail of the A vector. That is, the tail of the B vector will coincide with the tail of the A vector, and accordingly, if we find out that that their heads also coincide, then that simply means that A and B are equal. And suppose when we shift B and the tail of B and A is coinciding, but we find out that their heads are not coinciding. Either the direction of B must be different, or the magnitude of B must be different. So these vectors A and B will said to be unequal. So how we write is if their magnitude and direction both need to be equal, then we write the vectors A and B are equal. Then coming to the next topic, that is coming to the unit operations of the vectors. As we discussed, the unit operations of the scalars, they are simply the rules of ordinary algebra. But with the vectors, this is not the case, because here we are dealing with the directions also. So let's introduce the topic, addition of vectors. So here we are going to discuss two laws which are very important. First is the triangular law of addition, and the second is the parallelogram law of addition. So first we will discuss the triangle law of addition. So triangle law of addition simply says that first let us draw the vectors. Suppose, and this is B. Here the name is very important because the which vector are we writing first, that is also very important. So first we'll name them A and B. So what we do in triangle law of addition is, like, we have to calculate A plus B. So first we will draw A. This is our A vector, and we place B. We shift B towards the A vector so that the tail of B will coincide with the head of A. Like this is B, and we will shift as if this is B. So here the tail of B, that is this portion, it coincides with the head of A, that is this portion. And then what we do is simply join the tail of A vector to the head of B vector. This is A. We have shifted our B vector in such a way. This is B. And this is our R, that is the resultant vector, which is A plus B. So here R is also a vector, A plus B. So this is as we are joining tail and the heads of the vector, so this method is also known as the head to tail method. So we can simply say that we have just joined the tail of A with the head of B, and here comes our resultant vector, which is A plus B. Now, you all must be aware of the commutative law and the associative laws of addition that are there in the ordinary algebra. Let me remind you, what do these laws say? Commutative law and associative law. In ordinary algebra, commutative law of addition simply says A plus B should be equal to B plus A. And associative law is said to be when the A plus B plus C is equal to A plus B plus C. Notice that I have not put the vector bar over the quantities A, B, and C over here because this law I have not written for the vectors. This law is only for the ordinary algebra where A and B, A, B, C, they are the scalar quantities. But now I would like to explain you all that why we cannot write these for the vector quantities. I want everybody to think and prove this on their own, and then we'll discuss it later in this lecture. Also, I would like to bring your attention that if we take two vectors, that is A and minus A, and add these two vectors, what would the result be? So as you guys all must have already guessed, the result would be 0. This 0 is because it is also because we are basically studying the vectors. So this 0 is known as a null vector or the 0 vector. Null or the 0 vector. So some of the properties that are related to the null or the 0 vector are as follows. When any vector A is added to the null vector or the 0 vector, we get the same vector. That is, neither the magnitude nor the direction of that original vector will change. When we multiply this null vector with any of the scalar quantity, or we can say a constant, we again get a null vector. Or when we multiply this null vector with any vector, we again get a null vector. So these are the simple multiplication and the addition rules for the null vector that must be somewhere useful, but they have a physical significance too. As we discussed in the previous lecture that about the position vectors and the displacement vectors. So we have seen that if there are 2 points, suppose A and some point B, so this is the initial position of the particle and this is the final position of the particle. And so the path of the particle can be anything, like this either can be a straight path or it can be some like this way, or it can be this way, any path. So we discussed that displacement does not depend upon the path taken, but it simply depends only on the initial and the final, that is only on the final A and B. So in context to the null vector that we are discussing, if suppose a particle goes from A to B through this path, here arrow denotes that it is going from A to B, and it again comes to B to A through some another path, arbitrary path. So here we will say, when we talk about the displacement, we know that the displacement is 0 here. So that's why that's the physical significance of the displacement. That's the physical significance of the null vector in terms of displacement. Here the displacement is 0, that is the displacement is, if D vector is a displacement vector, that will be here, that will be equal to the null vector. Now, as we have discussed the triangle law of addition, I would like to now go on to the parallelogram law of addition. So as the name suggests, in triangle law of addition, we were forming a triangle with the help of our two vectors, that is A and B. In parallelogram method, we will form a parallelogram using our two vectors. Let's see how these two vectors they can be used to form the parallelogram and can be used to determine the resultant R. So let's draw these vectors. We will take the initial same two vectors that were A, B. So in this parallelogram method, what we do is first, this is our A vector, and this B vector is shifted towards the A vector such that the tail of B vector must coincide with the tail of A vector. Initially, you must remember that in triangle law, the tail of B used to coincide with the head of A. But now it's the opposite. The tail of B should coincide with the tail of A. So here we will draw the B vector as this. So next step here would be we will draw a line which is perpendicular to A vector and starting from the head of B vector, which is parallel to the A vector and starting from the head of the B vector. See, this line is exactly A parallel to A, but starting from the B vector. And here what we will do is, starting from the head of the A vector, we will draw another line which is parallel to the B vector. So you can see that this is the parallelogram that we were talking about. And these are the 2 points. These are the two the vectors. They are coinciding at a point. We will join our original and this coinciding point. Now first let's name them. So this was our A vector. This was the B vector. Let's call this as the origin. We generally take it as the origin. And let's call this point as C. So you can see that this vector is parallel to the A vector. This vector is parallel to the B vector. And when we join the point of intersection of these two vectors with the origin, we get the resultant vector. So this is our resultant vector R, where R will be written as A plus B. So you can also check that from the triangle law of addition also, we got the same R. The R was of equal this magnitude and the same direction also. So these two methods are said to be equivalent. You can either use any of the method and the results will be exactly the same. Now coming to the subtraction. This is a parallelogram. And here we have not written our vectors. This was our A vector. And this was our B vector. Now coming to the subtraction of vectors. When we want to subtract two vectors, it's exactly the same. The only thing is, if we want to write A minus B, we simply write it in the form as A plus minus B. That is, we'll keep A as A is the same as the original one, and we'll draw another vector which is exactly of the same magnitude as B, but in the opposite direction as B. So we will get the resultant as A minus B. We can again here use any of the two laws, that is either the triangle law or the parallelogram law for our purpose. So let's first, so this was our A vector and this was our B vector above. We are taking the same vectors, and if we want to draw minus B, the minus B will exactly be in the opposite direction but of the same magnitude. So this is minus B, and then we will add these. So we'll use, I'm using triangle law of addition for this purpose. So triangle law of addition says we will draw A, and we will shift B, or we will shift here minus B in such a way that the tail of B coincides with the head of A. That is, we will shift like this, and then we will add these two. We will join these 2 points. So let us. So this was our A vector. This is the B vector. This is the minus B vector. And so here, this is the A, this is the minus B vector, and here we get A minus B, which is equal to R, resulting. Now, as we have discussed, the graphical method for vector addition, I would also like to introduce you all to the analytical method of vector addition. Analytical method of addition. So the thing is, sometimes complex calculations, they may lead to the confusion in visualizing vectors, and so the thing becomes time consuming. We discussed the graphical method because I wanted you to I wanted to give you an idea of what actually happens on a 2D plane when we add and subtract the vectors. However, in calculation, most of the time, we are going to use only the analytical method only. So let's start with the analytical method of vector addition. So, for starting, we may take A as AXI plus AYJ cap and B as BXI plus BYJ cap. And and when we want to find out R, which is the resultant vector, which is A plus B, let's denote as with a bar. If we want to calculate R, which is A plus B, we can simply write, and when we can take the terms in the I cap direction together, and we can take the terms in the j cap direction together. So this comes our resultant vector. So the x component for the resultant vector will be ax plus bx, and the y component for the resultant will be ay plus by. So this ax plus bx is rx, that is the x component, and this ay plus by here is ry, that is the y component. This method can also be extended similarly to more number of vectors and even to the three-dimensional space also, that is, which contains I, j, and k as the basis vectors. So in simple words, we can say there's this analytical method that when we resolve any vector A in two components, we actually want to know the contribution of the vectors in those two components, in those two directions, that is x and y. So when we add the two vectors, we simply add these contributions. That is, in the resultant vector will have the contribution in the x direction as the sum of the contributions of the original vectors in the x direction, and similarly for the y direction. Then we will come on to the next topic, that is the vector multiplication. Vector multiplication. Multiplication is of two types. First one is the dot product, or it is also known as a scalar product. We will see why it is known as so. And the second one is the cross product or the vector product. So first we will discuss about the dot product. So how we denote, like if we want to multiply two vectors, we will and we want to do a dot product. So we simply put a dot between those two vectors. Like as if in linear algebra, for multiplying two numbers, we use 2 cross 3. We here for the dot product, we will use a dot. It is known as scalar mainly because the result is a scalar quantity. That is, when we multiply two vectors using a dot product, the result will always be a scalar quantity. This result is a scalar quantity, that is, it has no direction. It is free of any direction. Now we will going to discuss the properties of the dot product of our unit vectors. That is the basis vectors that we that in our 2D plane, that's I and j. Properties. So the first property we can say that when the unit vectors are dotted, that is I and I, when the two same unit vectors are dotted, that is I dot I, that will give us 1, and j dot j will also give us 1 because they are same. And the second property says that when two different unit vectors are dotted, that is I dot j or j dot I, it will give us 0. So these are the two properties that will help us to lead to the result of the dot dot product. Now let's derive this. So when we write, suppose A, let us take A as E1 I plus A2 J and B as B1 I plus B2 J. And what we want is A dot B. So first writing it in simple terms, this dot b1I b2j. All these are caps denoting the basis vectors, that is the unit vectors. So so here when we have the this kind of multiplication as in algebra, as in ordinary algebra, we simply multiply this term with this term first, then this term with the second term first. So similarly here also we will do, but the only thing that we need to remember is that these are the constants. We don't need to put a dot between a1 and b1. The dot will always be between the unit vectors as we discussed in the properties. So we will write it a1, sorry. So we will write a1 b1 I dot I cap dot I cap plus a1 b2 I cap dot j cap plus a2 b1 j cap dot I cap plus a2 b2 j cap dot j cap. And now we will use our these 1 and 2 properties. So we will get to the result. We can see I dot I from above here. It's given as 1. So it will be a1 b1. Then here we take I dot j as it is given as 0. So it will be 0. Here also j dot I cap. It will be 0. So we will not write it. And here j cap dot j cap is 1. So we will write this term a2 b2. So this is our result of dot product of the two vectors a dot b. Now this derivation I showed you because this is the back-end procedure for the dot product, and you need to be aware of all the properties that are being used to get to the result. While when we actually do the problems and in the higher classes, when you will study more concepts related to the vectors, you will see that you don't need to do this back-end calculation always, because there is a simpler and a shorter method that is very easy, and it will give your answer quickly. So let's quickly see this shorter method. I don't want to erase this result. We will do here only, because I want you to know that the results are the same. So let's suppose this is our A vector, that was A1I plus A2J, and this was our B vector, which is B1I plus B2J. So for calculating A dot B, we can simply write it. We can simply write it in this way, like the components corresponding to I vector, I cap vector will be written one below the other, and here J cap also one below the other. And we can simply multiply, because we know that I dot I will always give 1, J dot J will always give 1, rest all the other multiplicative terms will give 0. So here we can simply write A1 into B1, A1 B1, and we remove the I because that is 1, and here we multiply these A2 B2. And even suppose if this was in terms of 3D, suppose we say if we extend it, suppose this A3 K cap, I'm doing this in 3D, it can simply be extended, and here it is B3 K cap. So the results would be the same, because see, with the same vectors dotted will always give 1. So here K dot K will also give 1, and here I dot K will also be 0, J dot K cap will also be 0. So here what we are left with is, we will simply multiply these terms also, that will be A3, B3 in 3D. So what we got is here A dot B will be equal to this thing, This is our result. We have simply multiplied the corresponding terms for the same i's, j's, and k's. So we can match this result as a1 b1 plus a2 b2. So this trick is simple and it's easy. And the best thing is that it consumes less time. So now we would stop here with the dot product, and we will discuss the cross product or the vector product in the next lecture. Firstly, we will today discuss some a few problems related to these to get you all thorough with the concepts. The first one is determine certain cross products between the vectors. Oh, sorry, we have not discussed the cross product. So we'll not discuss it here. We'll simply discuss the dot product today. Determine whether dot product obey the commutative and associative law of addition of multiplication or not, like ordinary algebra. And we have just seen that how these laws they are written. So here we will consider today only the dot product, and we'll discuss about the cross product in the next class. So first, coming to the commutative law. So for multiplication, commutative law simply says a dot b should be equal to b dot a. We are not putting the vectors because we don't know that if it is true for the vectors or not. Here a and b are only the numbers. So analytically, we can solve this analytically or graphically in both the ways. So for the graphical, we are going to solve it analytically as we just discussed the dot product. So we see if we want a dot b, we will write a first and then below that b because a is coming first. And when we dot product it, we will get a1 b1 plus a2 b2 according to the short trick that we just discussed. And similarly, if we write b vector first because we want b dot a, so we will write b first and then a. This is in 2D. So here b dot a will give b1 a1 plus b2 a2. So you can compare that the results are exactly the same. Therefore, we can say that a dot b is equal to b dot a for the case of vectors also. That is, the vector multiplication also follow the commutative law of multiplication. Now I want everybody to find for the associative law of multiplication. We'll discuss it in the next lecture. Now we'll move on to the next problem. So this is a lengthy derivation problem, which is very important for the practical applications. That's why I am deriving it in the practice problems only. So the problem says find the magnitude of the resultant of the two vectors a and b in terms of their magnitudes and angle between them. So see, this problem basically says that in the last lecture we had studied the vector addition also. So that was in terms of like if we are given any vector in terms of x and y, that is in the Cartesian coordinate system. If we are given in terms of xi plus yj, then we can simply add them analytically. But here if we are given the vectors in terms of r and theta, that is we know their magnitude and their direction. And then we want to calculate the resultant, then what the answer would be. So here we are going to calculate that. First make a diagram related to it, because we always know that we should always make a diagram first in these kind of problems to avoid any kind of confusion afterwards. So let's we'll take any arbitrary vector. Suppose this, and we quickly write what this actually means. So here our vectors are a and b, whose resultant we want to calculate. A and B, and their magnitudes they are known. That is, this is A, this is B, this is the resultant R that we have to calculate. This is the angle theta. This angle is the angle theta between A and B. That is also known in the question. This angle is the alpha, is the angle that this resultant vector it makes with this A vector. We are taking it that way. Now, for the purpose, we can say this O, it's Q, it's the point S, it's the point P, it's the point N, and this is the perpendicular. This is simply, this Sn is simply the perpendicular to OP or ON. We'll need it in our geometrical calculations. This is also theta because simply we have here we have found out the resultant using the parallelogram law. So this OS is the resultant vector and this is the parallelogram. So this theta will also be same. So here we will start with the geometrical derivation. Here we can see in this right angle triangle, this OS and N, we can use the Pythagoras theorem and we can write OS square is ON square plus SN square. And here we know that ON is simply, we do not know the length of ON, so it can be broken down in terms of P, OP plus PN. OP is A, that is here A is the magnitude. PN is simply B cos theta. Because you can see that this vector is simply the length B, because they're simply parallel. And then similarly, Sn can be written in terms of B as B sin theta. And when we put these values in our Pythagoras theorem, we get on adding and our resultant R will be OS will be equal to, on opening these brackets, we will get A square plus B square plus AB cos theta. So this is the magnitude of R that we wanted to know, that R, the length of R will be this. So here you will also be aware that this equation, it's basically the law of cosines that you all must have studied in your mathematics or trigonometry also. Now, if we look for finding out the angle, we'll first look in triangle OSN. We will get Sn is OS sin alpha, which is R sin alpha, and in the triangle PSN, if we look, Sn will be PS sin theta, or PS is basically B, so it will be B sin theta. And because Sn here are both equal, and when we equal them both, we will get R by sin theta, B by sin alpha, or we can say sin alpha can be written in terms of sin theta. That is, theta we know, D we know, resultant we have calculated, and alpha is unknown. So this alpha can be calculated using these values. So this way we can also calculate alpha. So we have calculated this resultant, the magnitude of the resultant vector, and we have also calculated this angle alpha, that is this resultant it makes with the vector A. This can be calculated. Here we can also derive the law of sines as we have derived the law of cosines. Also using trigonometric calculations, we can see that tan alpha will be in this triangle, it will be Sn divided by OP plus Pn. So it can be written in terms of theta also. Pm would be A sin alpha and B sin beta. Beta is this angle. And with this relation, we can also find B by sin alpha. So overall, if we write, combining this relation and this relation, we can write R by sin theta, A by sin beta, B by sin alpha. And this whole equation, equality, that we are equating different quantities, that is known as the law of sines. We have simply used the geometrical and the trigonometry, geometry and the trigonometry over here to firstly find the value of r, that is the magnitude of the resultant vector, in terms of the values which are given to us. And also we can find out this angle alpha in terms of the values which are known to us. So you will see that we'll also discuss a question or a practice problem in the next lecture, which will make us aware of practical use of these formulas, because we will see in most of the problems ahead that we generally know the magnitude and the directions of the vectors, and we are not given vector in x and y form. So when such questions are there, we would like to use these formulas only rather than deriving everything again. So these formulas, they must be memorized, or even if not memorized, they must be you must be aware of this kind of derivation. We'll end the today's lecture here, and we'll carry on with the cross product in the next lecture. Thank you.